Hello and welcome to Artificial Intelligence on AWS as part of the AWS Innovate online conference. My name is Sean Ray and I'm going to give you a crash course in one of the hottest technologies in the world at the moment, artificial intelligence. Once the domain of research labs and universities, has found its way into the hands of the biggest technology companies across the globe. If you are new to artificial intelligence, don't worry. I'm going to take you step by step through the current trends, applications, and what it means for your business. Specifically, we will explore some common questions and technologies used in real-time, real-world examples, so that questions such as what is AI, how is AI being used in business, and what does this have to do with deep learning can be addressed. My goal is by the end of this presentation, you will be able to answer these questions and more. Artificial intelligence is not new. In fact, the name was coined in the 1940s, and the technology that underpins some of the most powerful artificial intelligence algorithms was discovered in 1960. But it wasn't until the advent of platforms such as Facebook, Google, and Amazon that it was necessary to use this technology to solve problems. These problems were so large that Moore's law has only just reached the apex of compute power needed to solve these big data challenges. So now, in search algorithms and online shopping recommendations, applications such as fraud detection, we see these algorithms conceived of almost 50 years ago are now in common practice. All powered by machine learning. But what is machine learning? Put simply, it is the ability for machines to learn without being programmed by input. Much like a baby trying to walk for the first time, we expect the machine to figure out how to place its limbs, how to balance its body, and propel itself forward while striving not to fall. At Amazon, machine learning has been key to many of our business processes, from recommendations to fraud detection, from how much inventory we keep, and to understanding abuses on the platform. This is just a small insight into the many application areas such as search, autonomous drones, and robotics in fulfillment centers, where we use machine learning extensively. Among machine learning solutions, a class of algorithms called deep learning has come to the forefront in solving problems. These problems need to be able to absorb huge volumes of data. For example, detecting a face inside a photograph, the meaning of a word in a paragraph, or the intent of a spoken word to a home automation device. To understand why machine learning is so powerful, let's look at a common set of problems. In this slide, you'll see a Rubiks Cube. It's a puzzle game where the goal is to match all colours on the 6 sides of the cube, accomplishing this by twisting and turning the outer rings of the cube. If you are doing this in isolation, it is quite simple to look at the cube and twist and turn it until you find a solution. But what if we needed to solve the cube for someone else? If we think about the steps we need to take, first we need to look at the cube and the state of the cube. We need to decide what colours are on each side. And then we need to think about the twists and the turns that we will make with that cube so that the coloured squares can move to the location on one face of the same colour. You need a way to convey the instructions to your friend who wants the cube solved. So you invent a shorthand style of writing down each move. In fact, there's a global standard for writing down Rubiks Cube solutions, and it looks like this. Each face and each twist is denoted by particular combinations of letters and numbers, so you can now link to the cipher on the internet and your friend can take your instructions and solve the cube. You solve your friend's cube and write down the instructions for them, but now your other friends have heard that you are great at solving Rubik's Cubes. In fact, it turns out amongst your friends that you are the best cube solver in the group. And now all of your friends want you to solve their Rubik's Cube. The problem, of course, is that each cube starts in a different configuration. So you need to solve all the possible configurations of a cube to account for the combination your friends are trying to solve. So you get to work on writing a computer program to do this. And once you have a basic implementation where your friend can input the current state of the cube, using notation we discussed before, the program will try and solve the cube. But you realize it takes a long time to find a solution. So you decide to solve all the combinations of the cube so that you can pre-calculate the answer. A Rubik's Cube has 6 sides and each side has 9 squares. But this is not a good way to think about the cube. When trying to count the number of positions, instead we need to understand how the cube is built, what types of pieces there are, and how each piece moves around the puzzle. It's important to understand that the Rubik's Cube has 3 types of pieces. Each behave differently as we turn the sides of the cube. We'll keep this in mind as we do our calculations. When you twist a cube, you might notice that the center piece never moves. It's on a fixed axle. All the other pieces rotate around that fixed axle. As there are 6 sides, we know that there are 6 center pieces, and they only have one orientation because they're fixed. Every 3-dimensional cube has 8 corners, and the Rubik's Cube is no exception. Unlike centerpieces, each corner can be moved and rotated. Since we have 8 corners, our total number of permutations for these pieces is 8 factorial. To figure out the number of orientations for a single piece, we need to count the number of stickers. A corner piece has 3 stickers. It must have 3 orientations. This means the total number of orientations for each position of the corners is 8 to the power of 3. Next, we look at the edge pieces. There are 12 edge pieces. Each piece may be moved or flipped. We can calculate the total number of permutations for these pieces as 12 factorial. We can use the same method that we did for the corners to determine the number of orientations. If we look at the stickers, it has 2 stickers, so it must have 2 orientations. So we have 12 to the power of 2 for the edge pieces. If we add the corners, the edges and the center pieces together, and we calculate the mass, you'll find that there are over 43 quintillion legal positions of the Rubik's Cube. We say legal because we're not going to pull the stickers off the cube and try and solve it. If you are not familiar with big numbers, the number scale progresses like this: millions, billions, trillions, quadrillions, and quintillion. So we're at the 5th order of magnitude. But let's put that in context with real-world examples. It would take 1,300 million years to see every position on the cube if you could view 1,000 per second. If we 3D printed a cube in each permutation, it would cover the Earth's surface 275 times. Not to mention the amount of resources we would need to 3D print that many cubes. Back to our problem. If we wanted to solve all the cube combinations for our friends, we could use a computer. Or we could use the power of several computers by using the cloud to calculate the combinations. It may surprise you to know that given the current compute power available, and the likely improvements we will continue to enjoy through Moore's law, it would still take 35 years to solve the Rubik's Cube. So if we can't solve the Rubik's Cube, how do we solve complex problems like the Rubik's Cube? We don't have 35 years, so let's look at how history has accomplished similar tasks. If we start with board games, and specifically tic-tac-toe or noughts and crosses, depending on where you're from, 10 to the power of 5, legally about 20,000 moves, arbitrarily solved by your phone. As we move up the scale, we have the Rubik's Cube, 10 to the power of 18, or the number 1 with 18 zeros. And we know that it would take 35 years of compute brute force to solve all the combinations of the Rubik's Cube. Next we have the game checkers, 10 to the power of 20. It doesn't look vastly more complex than the Rubik's Cube. People have attempted to use brute force to approach to solving checkers. After 14 years, they had only solved a portion of the combinations. And then we have chess, probably the most famous complex game. Numerous researchers, governments, and companies have tried to solve the game of chess. In our solar system, the sun heats the planets depending on their proximity. It is estimated that the sun will continue to do this for about the next 100 million years. Once the sun dies, the Earth will cool down and life will cease to exist as we know it. This is known as the heat death of the Earth. Researchers have calculated that to solve the game of chess using conventional computing, even if we include the gains that we'll get from Moore's law, it will take longer than the heat death of the Earth. And finally, we have the Chinese game of Go. It's infinitely more complex than chess, conceivably not solvable without quantum computing, at 10 to the 360. So what do we do when we can't solve a problem? We need to look for an alternative way. In fact, if you look back through history, you'll find that the game of chess was somewhat solved in 1996 by a computer that played against probably the greatest chess player of all time, Garry Kasparov. And then in 2016, a computer beat one of the world's best Go players, Lee Sedol, a 9th Dan ranked player. But we know that computers haven't solved all the combinations, so how did he manage to defeat some of the greatest players of our time? Instead of brute force, these systems using another technique, and it's called machine learning. Special algorithms that learn the same way humans do, applying vast knowledge banks of previous games. and with each cycle, they are trying to increase the probability of the game outcome becoming a win. These systems are trained using a technique called deep learning, and they are applied to an artificial neural network. An artificial neural network is similar to how our neurons in our brains are designed. These systems are pre-trained by ingesting large volumes of data, so that when they enter the game, they already have an idea about which move works best in which situation. Now let's look at a common application of deep learning. In order to solve our Rubik's Cube, we need to be able to visualize the cube and understand its current state. For this, we're going to use image recognition. Then, we need to tell our friend how to solve the cube. For this, we'll use natural language. Finally, we need to be able to hear from our friend if the cube was solved. And for this, we are going to use speech recognition. Amazon Rekognition is a deep learning-powered artificial intelligence service that lets you upload photos and the system will automatically tag objects, scenery, and faces. For example, it can detect if a person is smiling or if they are wearing sunglasses. But it's not just limited to faces, it can also detect everyday common items such as bikes, tables, and chairs. We'll use Amazon Rekognition to detect a face in our demonstration. Following that, we'll use Amazon Polly, a text-to-speech service that will become our user interface. It will let our renter know when to take a photo or when the door is unlocked. We'll use Amazon Lex, our natural language processing service, to provide an authentication code to our smart lock demonstration. To demonstrate this technology, I'm going to simulate a facial recognition system that you could use for a rental house. A common problem facing people who rent out their house on sites like Airbnb is that you need to meet the renters to give them keys. But due to delayed flights or traffic in your area, owners are often left waiting several hours till the rentee to turn up. To solve this problem, we are going to use all three of the artificial intelligence systems we talked about earlier: image recognition, voice recognition, and text-to-speech. This demo is going to use some technology that a lot of people are talking about right now. The devices running our code are Internet of Things devices. This means that they connect to the cloud and send and receive data both from systems in the cloud and also from sensors in their own devices. Today we'll be using a Raspberry Pi. Inside the case we have a mini computer. It has USB ports, Wi-Fi, a CPU, and memory as you'd expect on a computer. Today we're using version 3 of the Raspberry Pi. Importantly, this one has built-in Wi-Fi, so we don't need to provide a dongle or Ethernet connectivity. The Raspberry Pi runs on ARM architecture, meaning that it is not compatible with programs we write for our PC or our Mac. In this case, we'll be using C code to communicate between the Raspberry Pi and the AWS cloud. We can do this because AWS has a software development kit for most common languages, C included. The Raspberry Pi will provide the smarts for our AI door lock. On the ribbon here, we have a camera. It's just like a normal webcam that you can use on your PC. But because I use the Pi for lots of different demos, this embedded camera is more useful for this purpose. The camera will allow us to take a photograph of the person who presses the doorbell in this demonstration. We're also using a microphone. It's important to note that the Raspberry Pi does not have a microphone built in, so we'll be using this microphone to verify an SMS code that is going to be sent to our phone. If you're building an embedded device, you would choose something much smaller and much more industrial than I'm using here for this microphone. But for this purpose, it saves me from bending over on the table. And finally, we have the audio cable. This is a standard 3.5mm audio cable. It is male on both ends so that we can record the sound from the Pi as we go through the lock system. Normally this would be connected to an external speaker, but here we have it plugged into the recording studio equipment. That's all the components of our setup. So now let's get into making the AI door lock work. Now we have connected up the aforementioned components and we'll kick off the live demo. The Raspberry Pi and IoT button are connected over Wi-Fi to the AWS Internet of Things service. They've been registered with the service and we have set them up with our required security certificates. We don't want unauthorized devices connecting to our network, so AWS provides the security as part of its platform. To show you what is happening in real time, I will now subscribe to the IoT topic in the console. Here we have opened the IoT service and we have gone to test this device, as the device is pre-registered. We will subscribe to the lock commands topic. Topics are channels for each Internet of Things device. If you're familiar with something like Slack, just think of them as different rooms or channels that you can post messages into. We can have multiple per device. For instance, on this Raspberry Pi, in addition to the commands channel, I have a channel called IP that lets us know the IP address of the Raspberry Pi once it connects to the Wi-Fi so I can SSH into it. At the moment, there is nothing in this channel, so we will wait for the Raspberry Pi to boot up. Once the Raspberry Pi comes online, we'll see a connection message letting us know the doorbell is ready after boot up. Okay, we've connected to the door lock. So our Raspberry Pi is up and running and waiting to service our Airbnb rental. Now we'll simulate pressing the doorbell. By pressing the IoT button, we can send a message to the IoT service to tell the Raspberry Pi that someone is at the door.
Welcome. Thank you for pressing the doorbell.
It will take a couple of seconds to activate.
Thank you. I am now verifying you are a guest.
Now, how does Polly know that I'm on the guest list?
I will now scan your face. In 3, 2, 1, click. You are not an authorized person. The police have been alerted. Run away.
Okay, so we need to add ourselves to the guest list. We've opened up the S3 console, and in this bucket we see a picture already there. However, it is not a picture of me, so first we need to delete this picture. Next we're going to upload this selfie.jpg picture from my desktop. Once it is uploaded, we need to rename the photo to authorizeduser.jpg, as this is what the door lock is looking for. The code looks for this photo when comparing the photo that the door takes when the bell is pressed. It returns a confidence level that the person it took a picture of matched the authorized user JPEG image. In this case, I have asked the system to approve the facial recognition if the confidence level is higher than 85%. So we've renamed the JPEG, and now we can go back to our demo. By pressing the doorbell again, we can attempt to verify our face with the new authorized user picture. It will take a couple of seconds to activate.
You are on the guest list. I have sent an SMS to your phone number.
Because the photo of our face matched the 85% confidence level we have predefined, we have been sent an SMS to our phone number. Once the SMS is received, I will speak it into the microphone and a security code. The Raspberry Pi will check the security code. If it matches the one I sent, it will authorize us and open the lock.
Please speak your security code.
Okay, so now I have received the SMS code, and I will speak it into the microphone. 7139.
Thank you. That code is correct. Welcome to your rental house. I have unlocked the door.
Now we can look back through our IoT channel and see that each step, either the IoT button or the Raspberry Pi, were posted their commands. They've posted it into the channel so we can see what is happening. It's very useful for debugging purposes. We also posted the security code through the MQTT client into the commands channel. This is useful if you're performing a demonstration of services in a country where SMS is expensive or not available from the cloud platform. One part of the demonstration that needs a little further explanation is the security code. You will notice I spoke into the microphone the security code I received through my phone via SMS. This speech was actually recorded by the Raspberry Pi. It was then sent to the Amazon Lex service, which performs natural language processing on the recorded sound file. It then translates this into my selected language, in this case English. The spoken words 7, 1, 3, 9, once they have been processed by Lex, they are sent back to the Raspberry Pi for verification. If the code matched the original one, like the case we just went through, the Raspberry Pi verifies the user and opens the lock. Amazon Lex is a powerful artificial intelligence service that can translate spoken word, text or other inputs. You can use it to create chatbots for Facebook or Slack bots for your operations as well. Or you can use it to perform speech recognition like we did here. To recap, we used facial recognition through Amazon Recognition to authorize renter based on a photo they uploaded when they registered for the house. We used Amazon Polly to translate our computer text into speech so we could communicate with the renter. And finally, we use Amazon Lex to verify our security code through an SMS. This is an overview of using artificial intelligence to solve real-world problems. Amazon is democratizing AI. Whether you're a student living in your parents' house or the largest enterprises in the world, we want you to have access to the same technology that power the largest technology companies. We are very passionate about AI. At Amazon, we will continue working through our Alexa technology, enhancing our speech recognition and natural language processing. So we can detect the intent of users who want to book a flight, or book a car, or order a pizza. We have used 3 sensors, see, hear and talk, as part of our AI journey. But there is still one more part of AI that is still progressing. Robotics. Through our Kiva robots in our factories and our drone deliveries in the UK, we are working on new robotic technologies to make businesses more efficient. Artificial intelligence is not new in Amazon. In fact, this is a snapshot of our website in 1996. As you can see from the red boxes, we had our first version of a personalization engine running way back then, some 20 years ago. Whether it's through Alexa technology, enhancing our speech recognition, or through Amazon Go stores where we use video recognition to track users and the groceries they buy, or through robotics with our automated drone delivery. We are striving to democratize AI for everyone, pushing us towards not just specialized AI that can play a single game, but general intelligence that will allow artificial intelligence systems to adapt to their environment and learn on the job. Oh, but what about our Rubiks Cube problem? If we apply deep learning to this problem, it can solve the Rubiks Cube in under a second. As you can see from the video, the system is using multiple cameras. It is checking the state of the cube. Then it is applying its algorithm and figuring out the solution. Finally, it is using high-torque electric motors to solve the cube at lightning speed. For those of you who missed the first time, I will play it once more so you can see how fast all of this is occurring. In this talk, we've used deep learning to simulate a lock with facial recognition. We've seen how AI can be used to solve a Rubik's Cube in under a second. And finally, we have seen real-world examples such as Amazon Alexa, our Amazon Go store, and drones using deep learning and artificial intelligence to change our daily lives. If you are interested in artificial intelligence, please subscribe to our blog at aws.amazon.com/blogs/AI. If after today you want to take your AWS knowledge to the next level, you have several options available to you. To gain more confidence and hands-on experience with AWS, watch our instructional videos and explore the self-paced labs. Additionally, you can attend our instructor-led courses qualified by AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. And finally, don't forget to validate your technical expertise with AWS and use your practice exams to help you prepare for AWS certification. You can get more info on all of these three options at aws.amazon.com/training. And finally, I'd like to thank you for attending today and sticking it out to the very end of the presentation. Take the time to provide feedback on today's event so we can enhance our events experience for you. I also wish you good luck in using AI to build smart products and help unlock the true potential of your business. That is artificial intelligence. I am Sean Ray. Thank you very much.